Well, I finally did it. I finally made it happen in microcap. It took a lot of doing, and it's not exactly the way I expected it to be. I'm not recharging the battery. I'm actually oscillating current through the battery so that it's both positive and negative. Now, somebody told me secondhand from somebody else that you're not supposed to do that. I don't see why not. It massages the battery. Except in this case, thousands of amps and thousands of volts. Yeah, you're not supposed to do that. That's why. Oh, so we don't use a battery. We use a solar panel or something similar. Probably crack the solar panel. We use something. The battery helps regulate things because, you know, the tendency of free energy is just to explode in your face. Now, I ran a simulation for 1,340 seconds, and I managed to get teravolt. No, excuse me, more than that. What comes after tera? Whatever comes after tera. I think it's peta. Peta volts. Yeah, 6,000 teravolts. Let's put it that way. That's not bad. And I'm back to the good old scheme. I can't do the whole thing. I'll have to shrink it. There. I'm back to the good old scheme of putting a spark gap between two capacitors, and then I go to ground, though, in this case, and that represents the sphere grounded to virtual reality. It was the only way I could do it. I got diminishing returns if I just had a capacitor in ground. I had to put a spark gap. I didn't try one capacitor, but I just assume I have to sandwich it on both sides. And then I took out all my other capacitors that were sandwiching these components. So now I just have resistors. Still have a diode here, but I realized I got it wrong. It's pointing in the direction. Let's get rid of these. It's pointing in the direction. Whoops. It's pointing in the same direction as the circularity, clockwise circularity of the battery. So what good is that? Well, if I did it the other way, I didn't get as much power. And yeah, everything was negative. And no, I had to put it in line with the battery. Of course, in opposite polarity, and then the battery would recharge. But then it was like nano amps. Okay, a trickle charge, and that reduced the current and the voltage throughout the whole thing. And I thought, no, I want more power. Is that the idea? Well, yeah, you're trying to run a motor, so you want more power. So somehow this thing has to be cut off quicker than 1,340 seconds in order not to blow a fuse or over voltage the motor. You know, the motor will start speeding up too much and give everybody, the passengers, whiplash. And that is a problem. When something surges so much, how do you prevent whiplash among the passengers? Maybe coupling the coils to a larger magnetizable mass just might help. Let's see, what else? I had negative coupling coefficient in here, but it actually was diminishing performance. So sometimes negative coupling coefficient helps the circuit, and sometimes it detracts. And in this case, it detracted. But I still kept the capacitor over here, the diode, the resistors, so all that's the same, and the coupling coefficient is 0.7, so 70%. And the coils, what are they? Are they 1 Henry? Yeah, 1 Henry on the coils, and then on this load coil, it's 1 Henry. So all 3 coils are 1 Henry. Now the capacitors, I lowered them to, I think it was 1 pico. No, I had to lower them to 100 femto. That seems to work pretty good, 100 femto. A plate of glass, you know, something like that. So all the capacitors, and not too many, there's two on either side of the spark gap representing in its entirety a hollow sphere. So the only spark gaps I have is just one over here on the side. Excuse me, not spark gaps, capacitors. Is one over here on the side. The battery is a 6-volt battery. The resistors are 1 ohm resistance. I didn't even bother to do 100 milliohm. Figured, what the hell, you know, it's not going to matter either. I need them in there, but why be so particular? You know, not be humongously weird, or extremely scantily weird. 1 ohm. 1 ohm sounds good enough. And it's pretty hard to get high voltage resistors that are not 1 ohm. Something other than 1 ohm. Good luck. So I'm assuming this is the motor, and that this is the transformer pair of coils inside the steel drum of the Ammann Brothers setup. And inside that steel drum are these other components of maybe a capacitor over here of some sort, and some diodes, some baking soda or borax diodes, with an aluminum anode and maybe a lead cathode. So it really is a simple circuit. So the capacitance of the copper spheres has to be no more than 100 femto farads. I mean, I originally had 10 microfarads, and it was way too high. And the reason what cued me on that was too much was the wavelength was humongously long. And I thought, this isn't right. I mean, good grief, it's unbelievably a long wavelength. So I realized I had to lower the capacitance to increase the frequency of oscillations in this LRC circuit, and lo and behold, and then also increase, test again for lengthy durations of simulation, and voila! Instead of getting diminishing returns, subject to thermodynamic losses, instead I got surge towards infinite oblivion. So it's funny, you don't necessarily have to do an Eric Dollard analog computer circuit. There are a lot of different ways to overcome the thermodynamic limitations of a traditional, conventional LRC circuit. And you just have to understand that frequency is very important. It's more important than anything, because thermodynamically speaking, you're losing energy per unit time, and you've got to overcompensate by raising frequency more often than not. Now, in certain circumstances, you can raise both the capacitance, most importantly, along with the inductance to support it, to play a supporting role, and then you can get over unity, because you've worked with capacitance and inductance. But we want something scalable down to a reasonable size. We don't, well, in the case of capacitance, it's going to be very scanty, right? But the coil is going to be humongous, and we don't want that. So we got to be reasonable, and so the only other factor you can deal with is frequency. But frequency is manipulated indirectly by virtue of the fact that this is a DC battery, and so we're setting up oscillations not based on any kind of sine wave input function, like a radio tuner or a sine wave generator or anything of the sort. Instead, we have to depend on the oscillations set up by the capacitors. Now the coils, I set them up based on practicality. I always assume that for stability's sake, the transformer coils have to be large. That does not mean they have to be. They could be 100 millihenries each, but I just put in 1 Henry and I didn't need to change it. So, and I put in 1 Henry for the motor coil, the load coil, even though, well, that's pretty close to what an AC motor in an EV will be anyway. It seemed to be arbitrary. Basically, the load seems to be arbitrary. What matters are the capacitors, because they are what's driving this thing. Now, I had to do, in order to minimize matrix's singular error, I had to vary all the parameters of all the components except the diodes. The diodes are the only ones you can't get away with varying them, because you'll kill the over unity. Whoopsie! And Talk about lack of realism here. Yeah, they. That's one of the quirks of overunity in a simulator modeling software program, is that if you get all the parameters exactly the same, you can easily get overunity, because you've got like a ringing bell situation. You got resonance, but how realistic is that? Every component is slightly different than another when it's manufactured. They make it according to certain minimums and maximums of error, or variation I should say, but they still vary, and the simulator doesn't know that. So that's not realistic. Once you start to vary components, you start to kill the overunity in many cases. Well, in most cases, just about all cases, except when it comes to spark gaps. You actually enhance the situation if you start to vary the capacitances of the gap when it's not arcing and when it's arcing, without necessarily changing. In fact, I didn't get good results by changing the capacitance of the spark gap electrodes in any major way, but in a minor way, like 4 zeros. It was 1 picofarad for the gap capacitance and 3 picofarads for the arcing capacitance for both spark gaps. So I added 4 zeros to the right of the decimal point, so it's still 1 and 3 picofarads. And then I added a few digits of numbers, about 2 or 3, I think 3 digits of numbers in addition to the 4 zeros. And then each one was varied, what those 3 digits were attached to the 4 zeros, making 7 digits in all of precision. And that gave me, I believe, a boost of performance. And that generally is what happens when I do that. So that's a good thing, in which variation doesn't kill your overunity, it actually helps it. So essentially, because of the 4 zeros, I'm assuming I didn't change anything intrinsically or generic, in a broad sense when you're dealing with something like this. A spark gap that's going to have variations of the behavior of how it behaves anyway. I just wanted to make sure the simulator knew that each spark gap was very unique in its parameters, or at least minimally unique, because I don't know how to vary anything. And I'm afraid, actually, I think I've done this before, when I vary the other parameters of the spark gap, it kills the overunity. So I found, I think I'm better. So you see, I fudge, right? I'm not trying to be totally realistic because I know it'll happen. So I still don't know whether this thing will work, but at least I got it to work in the simulator, and it was bugging me to no end of how am I going to get this to work, because it worked in Paul Fawcett's simulator, easy as pie. But in here, it was very difficult. Only because I didn't spend enough time with it. I was in a rush mode, and you cannot rush. You've got to plod along like Edison and try 10,000 options, all of which fail, and then the 10,001st works when you think you've exhausted all options. You've really got to be patient with this thing when you don't know what you're doing. And that's the only way I learn anything, is to assume the truth, honest to God truth. I don't know what I'm doing. It's only the long hours I spend at it that gives me anything to work, to bank on. Knowledge by way of lots of failures. What else can I say? So this is my presumption. Now, I don't know what will happen if I take out this diode down here, because there's nothing that says it has to be there. I think in Paul Fawcett's simulation I had to have it there. It boosted performance, that was it. Yeah. But I didn't have this makeup. I just had one capacitor, so I could try that, take out that diode. I know I gotta have one diode somewhere in the circuit, but because I'm assuming that's what they had, was a borax component, that was the mineral, the mysterious mineral in question was either trona or borax. Trona being sodium sesquicarbonate, which is a combination 50-50 molar ratio between sodium carbonate and sodium bicarbonate. I don't know. It doesn't seem to matter what the ratio here on this mutual coupling has to be, although it should be something from either like, what is it? I think 10% and above. If it gets down to 1%, the whole thing, the over unity collapses. I think that's what I found. So that gives a lot of wiggle room. So this could be a motor, since you got 2 coils, and they're free to vary within the limits of most motor coils, pair of coils. Of course, if you have a permanent magnet DC motor, that's a different situation. Then this ballast gets simplified or even discarded. I don't know how you model that. They have a DC motor in here, but I've never used it and I don't know how to use it. That might be interesting, is to see what I can do about that. Put a DC motor in here. And then I will have only 1 diode, and then it makes it easier to figure out where it goes, because there's only so many places. With 2 diodes, it gets complicated. So then I have to take a guess, and I don't know what I'm guessing, if it's right or not. I think that's the next step. Maybe tomorrow, because I've done enough work for today. I think I'm going to try to see if I can work with a DC motor. They have an example of a DC motor circuit, I think, because I don't know how to connect it. It has 3 connectors, and I'm like clueless. And they also have an AC motor as well, which is kind of interesting. If Tesla put in an AC motor, how would you adapt this to accommodate him? I don't know. Start with simple things first. Let's start with DC. But anyway, that's for tomorrow. So it's promising. It's looking good. At least I'm getting somewhere.